Hello, how are
Hi.
you?
Good.
Yeah. Uh, this is the first time you guys are like uh at the same time at the office hours.
Oh, yeah.
Yeah. Do you guys have any questions so far?
I was just wondering if you could go over like specific mechanisms.
Yeah, let's go over.
It's just the last ones. Let's see. Like dihydroxy addition, ozonolysis, and maybe carbene.
Mm-hmm. Okay.
Yeah, thank you.
Sweet. Mm-hmm. Yeah. So dihydroxylation is going to be the reagent with OSO4, right? The one that adds two alcohols on the same side.
Yeah,
Dihydroxylation. So the general reaction for that is going to be like, let's say we have an alkene like that, and we put that through osmium tetroxide, OSO4. And the second step is a reducing agent. So it could either be H2S or it could be NaHSO3 with water. What this will do is it will attach two alcohols onto the carbon on the same side. So it could be either both wedges, OH, OH, or it could be both dashes, OH, OH. Okay. So the mechanism is going to be something like this, like osmium tetroxide. That OS is bonded to four oxygens and it is double bonded to all these four oxygens here. Well, it looks kind of weird because this atom, osmium, has like one, two, three, four, five, six, seven, eight bonds. But that's what OSO4 looks like. Where let's bring in our alkene now, where one carbon of the alkene is going to attack one of the oxygens of the osmium. This double bond here is gonna go onto that osmium right there. And then once that happens, the other double bond here will attack the other side of the alkene. All of these three arrows happen at the same time, which is why this is a syn addition because they are forced to attach on the same face. So if they attach as the um, wedge, then both of them would have to be wedges. Or if they are both dashes, then both of them would have to be dashes. So based on that, let's say we have this here, and let's say that they attach on the front side. Both of them would have to be wedges like that. Then we have oxygens here with the osmium there with its double bond oxygens here. And from here, um, the mechanism, like the Professor Pascal Nasseri helix, um, this is still like a debate in current research as well. This is where the second step comes in. You do the reduction with H2S or NaHSO3, which just cleaves this osmium out and puts hydrogens there. But the bonds here stay the same. So since those are wedges, these would have to stay as wedges and put an OH there, which is why this is syn addition, right? So this is right here. It's just gonna be some uh chem magic for now, where he didn't go over the mechanism, so you don't have to worry about the mechanism for the second reduction step here.
Oh, okay.
Right. Uh-huh. Right. Or it could have been like instead of wedge, it could have been dash as well. But the important thing here is that this is a syn addition, and the product is vicinal diol. Vicinal meaning that the two alcohols are adjacent to each other. Diol meaning that there are two alcohols there. Okay. So that is the dihydroxylation mechanism where these errors here could be tested. Like, but then the second step here, we don't need to worry about that. Okay. Now let's go over ozonolysis, where the general reaction for this is that let's say we have an alkene, right? And the reagents are O3 as a first step. The second step, you usually see like um, methyl 2 sulfide or zinc with acetic acid. When I see this reaction here, I think of scissors, where I'm gonna cut this double bond in half. Right? Once I cut that double bond in half, I put oxygens in the middle like that. And the products I get are these right here. After the cut double bond, and I put oxygens in the middle like that. Right? Where these are two aldehydes because there are hydrogens here. Okay. So let's go over the mechanism of how this works. So we are going to draw out the O3, which looks like this here. Okay, there are three oxygens bonded to each other, where this oxygen here with one bond and three lone pairs of electrons are negatively charged. This oxygen here with three bonds and one lone pair is positively charged. And this oxygen here with two bonds and two lone pairs is neutral. So when we bring in our alkene, the oxygen with the negative charge is going to attack one side of the alkene. The other side of the alkene is going to attack that neutral side. And then this double bond here is going to pop off onto that positive charge oxygen right there. Okay, all at the same time. When that happens, it forms this kind of ring-like structure. Like let's say we have oxygen, 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 oxygen. Where now all of the oxygens in this crown-like structure are neutral. Okay. And now here's the weird migration step. I'm gonna label these atoms as 1, 2, 3, 4, 5. So this bond between atom 1 and 2 is going to migrate and make a double bond between atoms 2 and 3 to make that carbonyl bond right there, which is a carbon double bond oxygen. Then this bond between 3 and 4 is going to move to this oxygen right here, where these two electrons of that bond are going to move as a lone pair and give that oxygen another set of lone pairs. And from here, one of the lone pairs of the atom 5 is going to move right there. Right. So everything after those three arrows would look something like this. Let's say we have that H O O positive charge, negative charge. Let's say we have um So this was 1. This is 2, 3, 4, 5. Right there. Okay. And then from here, this O minus here is going to attack the carbonyl of the aldehyde right there. And then we know that that's going to break the octet rule. So we have to pop this double bond onto the oxygen right there, giving the oxygen a negative charge, where that negative charge oxygen is going to come back and attack the other carbonyl and push this up here. That double bond onto that oxygen right there. Okay. So let's see. When that happens, we are going to get so this is H O O carbonyl, and that's gonna be, let's say, O, and that is H, where this is gonna be 1, 2, 3, 4, 5. This atom 3 here is attached to atom 1 now because that atom 3 made a new bond between those two right there. And atom 4 here, this oxygen minus, made a new bond with atom 2, which is that new bond right there. And then that's the end of the first step. The second step now brings in the methyl, the 2 methyls on the sulfur, and it reduces everything to give us our final products here. Let's say the one of the lone pairs is going to attack this oxygen. That fix right there. That goes up here. And then this bond is going to attack this other sulfur at the same time, giving you there, say, there, and then sulfur. Where I'm going to highlight this oxygen is that oxygen right there. This oxygen is this oxygen, and this oxygen is that oxygen right there, right? Where we formed 2 aldehydes, which let's see if we form the correct aldehydes, which are these 2 aldehydes right here, right? And this is just the side product that gets formed right there. So this mechanism was really weird and complicated, but those are like the arrows on how to do that mechanism, right?
Do you think that Pascal is going to put that for the mechanism question?
I don't
Because he
think
did
so.
have one. Okay, because he had this for predict the products, but I wasn't sure if it was fair game for mechanism.
Yeah. It's most likely just gonna be used for predictive product and synthesis because you can use this for synthesis as well. There's not a high chance of the mechanism being tested here because I remember during
Okay.
lecture him saying like it's very complicated too, and he just like skipped over it.
Oh, okay, good.
Yeah.
Thank you.
hmm Okay. Where like we know that the trick for these predictive products is to make a cut in the double bonds in half. So let's say we have these double bonds here. This ozonolysis here will cut all of the double bonds in half. So imagine we get our scissors, we cut this double bond in half, put oxygens in the middle like that, cut the double bond in half, put oxygens in the middle like that, cut that in half, put the oxygens in the middle like that. These are our products right here. Right? Where you know how if they are not part of a ring and we cut that double bond in half, they separate into two separate molecules like that. But if they are part of a ring, like the double bond is part of the ring, when we cut that in half, they are still attached to each other. We just open up the ring into a linear chain. So this is no longer a ring because we cut it in half, but it's not a linear chain like that, right? This right here wasn't part of a ring, this double bond. When we cut the double bond in half, they separated into two separate molecules like that. Right? To make this like more aesthetic in the answer, we could number this 1, 2, 3, 4, 5, 6, where we know that we have a six-membered longest chain. So that's 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Where at carbon 1, there's an aldehyde. At carbon 2, there's this aldehyde group. Carbon 3, there's a methyl. Carbon 4, there's a carbonyl. 5, carbonyl. And carbon 6, there's nothing there. So that's one of the products. This is the other product. And the other product is this right here. We get three separate products. This product here, which is this product. This ketone here, which is this ketone. And this formaldehyde here, which is just a carbonyl with two hydrogens, which is that formaldehyde right there. Right. So that is ozonolysis. Okay. And which other reactions did you want the mechanism for?
Carbene, but then I don't know if you think that the mechanism is going to be something that's going to be tested.
Um, the carbene, let's see. It could be a conceptual question, like what it is and like why it is an electrophile. So let's just go over that really
Okay, thank you.
quickly. Let's say, let's see. So a carbene is going to be a carbon with 6 electrons, but it's neutral, right? Where it will have 2 bonds and 1 lone pair of electrons right there. The reason why it's neutral is because you know how carbon is on the 4th column? That carbon on the 4th column only wants 4 electrons to itself. So when we calculate the formal charge on this carbon, it has 1, 2, 3, 4 carbons, 4 electrons to itself. 4 minus 4 is 0, neutral charge. Okay, so but overall, this carbon only has 6 electrons, 2, 4, 6, meaning that it has an empty p orbital, right? Where this empty p orbital here makes this carbene an electrophile because it wants to gain electrons. This lone pair of the carbene makes that carbene a nucleophile because it could donate electrons. So carbenes are both nucleophilic and electrophilic. Okay. That is important because let's say that we bring in an alkene like that, and we react it with some kind of carbene, a carbon with 1 lone pair, 2 bonds, and empty p orbital. We know that this lone pair here can act as a nucleophile, which is going to attack one of the carbons of the alkene here. As that happens, the other side of the alkene is going to attack the empty p orbital. Like there's an empty p orbital there of the carbon because it's missing 2 electrons at the same time. When that happens, we are going to form a cyclopropane, a 3-membered ring like that. Right, where let's say this is C, this is R, R, where this carbon right here is that carbon right there, right? This could be H's as well. These bonds are syn to each other, the same side, because the alkene attacked the carbene the same time as the carbene attacking the other side of the alkene at the same time. It's similar to the dihydroxylation mechanism where this attacked at the same time. It's also very similar to let's say uh, an X2, like Br2. We know that the alkene is going to attack the bromine, kick out the other bromine, and then the bromine is going to attack the other side of the alkene at the same time, giving us a cyclic bromonium ion that are on the same side. So either both wedges or both dashes like that. This is because they attack at the same time. Very similar to how this carbene and alkene are attacking each other at the same time, giving us the same stereochemistry there. And there are three like different carbene reactions here, where the first carbene reaction that you'll see is with a diazomethane, which is CH2N2, right? Where let's say we have this alkene right there, and we put that through the diazomethane, CH2N2, under light or heat or some kind of metal like copper. This is going to create a cyclopropane ring, either that or this, right? So here's the mechanism. CH2NH2 looks something like this. Right? Where this CH2 right here has a full formal negative charge because it has 1, 2, 3, 4, 5 electrons to itself. 4 minus 5 is -1. So that's why it has a full formal charge of -1. This nitrogen here has a full formal charge of positive charge 1 because it has 1, 2, 3, 4 electrons to itself. But if we look at the periodic table, it's on the fifth column, which means that it wants 5 electrons. 5 minus 4 is +1, which is why that nitrogen has a positive charge, the nitrogen with 4 bonds. This right here is a really good leaving group. It's one of the best leaving groups in organic chemistry, which is just going to leave by itself first. It's going to leave as nitrogen gas, N2 gas, right? Which has a triple bond between them, like that, right? And once we have done that, we created a neutral carbon with 2 bonds and 1 lone pair. This right here is a carbene, which we just went over, a carbon with 2 bonds, 1 lone pair, and it's neutral. And we said that it has an empty p orbital because it's missing 2 electrons. So that's why this carbene here can act as both a nucleophile and an electrophile at the same time. Okay. Now let's bring in the double bond. This double bond here is going to attack the empty p orbital of that carbon because it's missing electrons. And at the same time, that lone pair is going to attack the other side of the alkene at the same time, giving us these two products here, where this carbon is that carbon of the ring right there with its 2 invisible hydrogens here. So that's one carbene reaction there. Another type of carbene reaction that you can see is with the Simmons-Smith reagent. So let's say we have this alkene right here. The reagents you see with that is CH2I2 with zinc copper. Right. So let's see. I think this is maybe the CH2I2 looks like this. Let's draw the C there with its two H's and its two iodines right here. Okay. The zinc right here will do an insertion reaction. It's going to insert itself between that carbon and iodine right there. When that happens, right, let's say that carbon there now has a zinc iodine because the zinc inserted itself between that carbon and iodine, which is right there. And that carbon is still attached to two hydrogens and one iodine, like that. Okay. And then from here, zinc I2 is just going to leave by itself, forming this carbene right here. Right. So this carbon right here is that carbon right there. It still retains its two hydrogens, but the zinc iodine and iodine left as zinc I2 right there, giving this carbon a lone pair as well, where this is our carbene, right? And then from that carbene, we do the same exact mechanism with the alkene that we have here. Since this carbene is missing electrons, one of the carbons of the alkene is going to attack that carbene. At the same time, the other carbon is going to attack the other end of the alkene, giving us these products here. A cyclopropane, where that carbon of the carbene is this carbon of the cyclopropane right there, with its two hydrogens here. If we made that cyclopropane a wedge, that forces the methyl to become a dash. It could have been the other way as well. That cyclopropane could have been a dash, making that methyl a wedge, right? Where that carbon of the cyclopropane is that carbon of the carbene right there. Okay. And then there's one last reaction for using carbenes, and that is using uh halogenated carbene. So let's say we have this alkene right here, react that with CHCl3 under strong base, like NaOH or KOH. So CHCl3 looks something like this. That carbon is bonded to three chlorines and one H like that. So we know that chlorine is really electronegative, withdrawing electrons from that carbon right there, which makes this carbon really partial positive. And that also withdraws electrons from the hydrogen, which makes this hydrogen extremely acidic and attractive to a strong base like hydroxide ion, which we do have here, KOH or NaOH, which the first step of this mechanism is to deprotonate this most acidic hydrogen and give that carbon a negative charge. Once we have that carbon negative charge, we are just going to kick out one of the good leaving groups, chlorine here, to relieve the negative charge. When that leaves, we have this carbene right here, the carbon with two bonds and one lone pair of electrons right there, right? And then the same exact mechanism happens where we bring in the alkene, gonna attack that carbene's empty p orbital. At the same time, that lone pair attacks the other end of the alkene, giving us this product here. But this time, this is a little bit different because that carbon of the cyclopropane is attached to two chlorines like that, right? So this is a different one than the previous ones because instead of hydrogens attached to the carbene carbon, we now have chlorines or halogens attached to the carbene carbon. So in synthesis, if you see two halogens on a cyclopropane ring, then you know that you want to use this kind of reaction here in your synthesis, right? Where you notice how all of these three examples here is very similar, where we have a carbene attacking the alkene at the same time as the alkene is attacking the carbene. That's the same exact like kind of mechanism, which does a syn addition all the time. Right? And that always forms a cyclopropane here on the same side, like both the wedges are both dashes, syn addition. And that is it for all the carbene reactions here. The first one was diazomethane. Second one was Simmons-Smith. The third one, halogenated carbene.
Okay, thank you
Uh-huh.
so much.
Yeah, uh-huh. Did that help?
Yes, thank you.
Yeah, uh-huh. That's good. Let's see. Any other questions?
If we could do like review about like for synthesis and stuff like that with all the reactions that we've learned, that would be great.
Oh yeah. So let's do some synthesis problems on this chapter. Let's say, okay. Let's see. Mhm. Okay, let's mix them up. Let's say we have, okay, let's start with a little simple one. Say, get that, ER. Okay, let's try this synthesis problem right here, where we're gonna start off with this haloalkane and then end up with this dihalide here that are anti to each other. Do you guys have any ideas on how to start this or how to go backwards from this?
Is it the BR2?
Yeah, Br2 in non-nucleophilic solvent or nucleophilic solvent as the last step. Yes, right.
I forgot the name, but it's like without that alcohol or
Yeah.
the, yeah.
Uh-huh. So this is gonna be Br2 without the alcohol or without the water because we added Br2 times instead of OH or OR. Right? Where you know how we added Br on these two carbons right here? We could assume that that came from a double bond right there. Right? So let's say there's a double bond right there. That makes this methyl forced to become flat and planar because that's an sp2 carbon right there. Right? Now, how can we create this alkene from this starting material here?
Strong base, strong nucleophile,
Yeah, strong base strong
alkene
nucleophile.
preparation, I think
Uh-huh.
is what it's called. I don't know.
Yeah, that's right, that's right, that's right. And what kind of strong base strong nucleophile do you want to use? An unhindered one or a hindered one?
Unhindered, right?
Yeah, unhindered, that's right. So it could either be like NaOH or NaOET, like any small strong base. Because we want to do an E2 reaction, which makes the more stable uh, double bond, right? We want to be able to grab this hydrogen here, make a double bond there, and kick out that leaving group to make that double bond right there. If we used, let's say, a hindered base like tert-butoxide or LDA, we are going to get that double bond right there. But that's not the double bond we want because we want the BRs here. Right? That's good. That's good. Okay. Let's see. Let's try something a little bit more involved. let's say we have now, okay, let's say we have, mm, ooh, this is, okay, let's do this. Okay, let's try this synthesis problem here.
A carbene for the last step.
Uh-huh. A carbene, and specifically the one with the halogens, right? Like the
Chlorine. Yeah, like
halogenated.
CH3Cl,
Uh-huh.
something like that.
Yeah, that's right. C, or let's say I think it was CHCl3. Yeah, CHCl3 in basic conditions. CHCl3 in KOH or NaOH. We know that that's going to come from a double bond right there, right? Because we want to make the um, cyclopropane with its two hydrogens, I mean, two halogens onto these two carbons right there. Right. Okay.
Would the carbene ever be in acidic condition?
It would not be in acidic conditions because the mechanism requires this deprotonation step to make that carbon a negative charge with a lone pair there. And then this leaving group will leave right there. So we get that lone pair for the carbene in basic conditions. If this was in acidic conditions, then this deprotonation step would not happen here. And we would not get that carbene.
Oh, okay. Thank you.
Yeah. Yeah. So far, these are like two-step synthesis problems, but we'll build up the difficulty after this here. How can we create this double bond from this alcohol here?
I'm not sure.
Uh-huh. So there are two main ways to make alkenes in this chapter. E2, which you know how our starting material for E2 is that we need to have a good leaving group, like either chlorine, bromine, OTS, OMS, or OTF. The other way is
Oh,
alcohol dehydration.
and that's E1.
Yeah, E1. And
Okay.
E2 also requires strong base. Alcohol dehydration requires strong acid. Strong acid and heat, right? Do you want to go over the mechanism of this reaction here? Or
Yeah,
does
could we
uh
go over that?
yeah, let's go over that where we know that our starting material has an alcohol. And if we put that through strong acid and heat, the first thing that we have to do is look for our most basic atom because we have a strong acid. Our most basic atom is that oxygen there with two lone pairs. So we are going to protonate that strong base with the strong acid that we have. Once we do that, we create this OH2 plus good leaving group here. Before this OH was a bad leaving group, we converted that into a good leaving group by protonating it with the strong acid here. Since this good leaving group is on a secondary carbon, it could just leave by itself in like a E1 like mechanism. When that happens, we form a carbocation on that carbon right there, which lost a bond, right? And whenever we form a carbocation intermediate, you always have to stop and look out for rearrangement steps. So it could either be, let's say, a hydride or methyl shift to make the carbocation more stable. So this is a secondary carbocation right here. If we look down here, if it moves there, that's also secondary carbocation. If we move up here, that could become a tertiary carbocation, which is more stable. But there are no hydrogens on that carbon. There's only methyl groups. So we're going to do a methyl shift here by shifting this whole methyl group onto that carbocation, which is going to give us this new carbocation right here. Since this carbon here used to have 4 bonds, 1, 2, 3, 4, but now it lost the bond. It only has 3 bonds now, 1, 2, 3. This carbon lost its positive charge because it gained a bond, which is from the methyl shift. And then from here, we locate all the beta hydrogens, which is, that's one choice, that's the other choice, and that's the other choice right here. And then from these beta hydrogens here, we choose the most substituted one to make the most stable double bond. The most substituted beta hydrogen is this one here because that carbon is attached to 3 other carbons. And it would give us the more stable double bond. So we use the HSO4 minus conjugate base to grab that hydrogen and make that double bond there in like the E1 mechanism, A1-like mechanism. And that forms that double bond right there, where this methyl group moved here. Right, that methyl group moved there. And then once we have this double bond, we could do the carbene reaction with the halogens to create this final answer here, photosynthesis.
And just to clarify, it can be any strong acid. So it could be like HBr or something like that.
Oh, so if it was HBr, right, that is a nucleophilic acid. It has to be a non-nucleophilic strong acid. Because if you used HBr, you would get something else. Like, let's say we use OH, HBr. The same first step happens. Protonate the most basic atom, which is that oxygen. Convert that into a good leaving group, OH2 plus. That good leaving group leaves by itself to form the carbocation. We form the carbocation, so we look out for rearrangement. In this case, we do a methyl shift to make the more stable tertiary carbocation. And from here, this is the different step here. Since we used a nucleophilic acid, right, we kicked out the Br minus. This Br minus is going to do an SN1 like reaction instead, which will attack that carbocation and give us this SN1 product here instead of like deprotonating the beta hydrogen and making the double bond. It would do an SN1 reaction, which this nucleophile would attack this electrophile, giving us this product instead. Right.
Oh, okay. So what other, like apart from H2SO4, what other strong acids would we see?
Another strong acid that you can see are like H3PO4, H3O plus. Yeah, these 3 here are non-nucleophilic acids. The most common ones are H2SO4 or H3O plus. Sometimes professor just put like H plus like that, but you'll most likely see H2SO4, and or H3O plus.
Okay, thank you.
Yeah. Where that non-nucleophilic acid, the reason why this HSO4 minus does not attack the carbocation is because that HSO4 minus looks something like this. Where you notice how the negative charge on the oxygen is really stabilized by resonance because it could move down there, pop the double bond up there, or it could do resonance down here. There's like a lot of resonance for this negative charge to do. That makes this negative charge stable and weak. Weak nucleophile. Since it's already stable, it's not reactive. and that makes it a weak nucleophile, which makes it not able to attack that carbocation right there. So it would just act as a base and do an E1 like mechanism where it deprotonates the most substituted beta hydrogen to form the double bond right there. Whereas bromine minus here is strong enough nucleophile to attack that carbocation right there to give us that product there. And this reaction here could be used if you wanted to, let's say, if we wanted to, if we start from here and then we went all the way to, let's say, and then do like that, right? Oh, wait, yeah, like that. Okay. Let's say this is OH. If you use HBr, we would get this product here, right? Where the mechanism that that does is right here. The OH gets protonated to become a good leaving group. That good leaving group leaves to form this carbocation right here. And then we do a methyl shift to form the more stable carbocation. And then that Br minus comes in and attacks that carbocation to give us that halo alkane right there, which is this right here, right? You notice how we added extra carbon chains? Back in 118A, what kind of reaction adds carbon-carbon bonds? How can we
Grignard?
extend? Yeah, Grignard reagents. That's right. Where we have a bromine here, the way that we can make a Grignard reagent from that is just to put Mg there, and that would convert this into a Grignard reagent here, where we know that this atom here directly attached to the Mg is the partial negative charge. So let's star that right there. Let's say that that starred atom is the star atom right here. Let's say that this dot atom, right, where the new bond between the star and dot atom is made, is the electrophile. So we have to make this an electrophile somehow. We have to make this a partial positive carbon somehow. And to do that, we can make this a partial positive carbon by attaching a good leaving group or a really electronegative atom like bromine there. Where the mechanism of this Grignard reagent is that this nucleophile is going to attack that electrophile and then kick out the leaving group. The star atom attack the dot atom, make a new bond between star and dot, and then attach what is attached to the dot atom. The dot atom is attached to 1, 2, 3 carbons. 1, 2, 3 carbons right there. So this could be another synthesis problem here. Okay.
I'm confused
Uh-huh.
on the BR. So you have the
Yeah.
MGBR, and because the Grignard reagent's MGBR, right?
Yeah.
So then why is it just BR with a carbon chain with it?
Oh, this one right here.
Yeah.
This is our electrophile where we have so you notice how this carbon here attached to the Mg is the partial negative charge, the nucleophile?
Yeah.
That nucleophile wants to look for an electrophile to attack. So this carbon here is positive charge because bromine is electronegative, withdrawing electrons, stealing electrons from that carbon right there. As that carbon is losing electrons, it is becoming more positive. So that's why this negative charge nucleophile here is attracted to that positive charge electrophile there. This is going to be a nucleophilic attack where that negative charge carbon attacks that positive charge carbon and it kicks out the leaving group bromine there,
Oh, okay.
right? And then when that happens, the star atom here is now attached to the dot atom. This is the new bond we made right here, the new bond from the attack,
Oh, I see.
right? And then this whole group here is that whole group right there that's still attached to the dot bond. And then we have Br minus floating around because that got kicked out after that reaction.
Okay.
Yeah. Let's do some more um, synthesis problems on this. Let's say we have let's say we get let's try this synthesis problem here. Oh wait. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. There we go. Okay. What we could do
Oh,
is
3.
1, 2, 3, 4, 5, 6, 7. Say this is 2, 3, 4, 5, 6, 7. 8, 1, 2, 3, 4, 5, 6, 7. Okay. Yeah. Okay. What can we do here?
The last step was the O3 mechanism.
Yeah.
Or yeah.
Ozonolysis, that's right. Which cuts up the double
The
bond
alkene.
alkene in half like that. That's right. And it adds oxygens in the middle like that, which will be 1, 2, 3, 4, 5, 6, 7. This 1, 2, 3, 4, 5, 6, 7 chain right there, right? Because after we cut it up in its original form, it should be cut up like that. But I redrew this whole thing as this, which is the same thing like that, right? Now we have to figure out a way how to make an alkene here from nothing. No functional group at all. So this is going to use some 118A reaction. If there's nothing on the alkane, what is the only reaction that this alkane can do? This is the very first reaction you learned in 118A.
Add a good leaving group, the light, like Br2 light or
Yeah,
something like that.
that's right. That's good. That's good. Where we specifically add Br because we want it to add to the more substituted carbon. That's good.
I
Uh-huh.
forgot, but is Br for tertiary or second? Like
Yeah,
which ones are for which?
yeah. Br is for tertiary, Cl is for secondary, fluorine is for primary.
Okay, thank you.
Yeah. Now, how can we convert this haloalkane into this alkene here?
Strong base, strong nucleophile.
That's right. And we want to use an unhindered one or a hindered one.
Hindered? Or
Uh-huh.
actually, I'm not sure.
Yeah, so you know how these are the beta hydrogens here, right? Which hydrogen do we want to grab to make the double bond? Which beta hydrogen?
The one on the right,
Yeah, the one on the right, which is more substituted than this one right here. So we want to use an unhindered base,
unhindered. Okay.
right? Which is going to be small enough to grab that hydrogen, make a double bond there, and kick that leaving group out for an E2 reaction, right? If we used a hindered base like tert-butoxide, TBU, okay, TBU, OH, that tert-butoxide, the really bulky base, is going to grab the most accessible hydrogen, make that double bond there, kick out that leaving group, and give you this double bond instead.
So that's essentially like the Hoffman product with, okay.
Yeah, that's right. This is going to be the Hoffman product. That's right. And this is the Zaitsev product. Right. And from here, like, right, like let's say we ended up with this by using the um bulky base. If we used like then the O3 to H2S, what kind of product would we get?
It would just cut it in half. It would be like a O and then, yeah.
Where in this case, we get two different products, the formaldehyde and the ketone on the ring. So if your synthesis problem gives you these two products from this reagent, this is the pathway you take using the Hoffman product by using the bulky base if you have these two products. But if you only have this one product here, we know that we want to make the alkene in the ring. Because you know how in ozonolysis, the reaction, if the alkene is in the ring, when it cuts it open, the alkene in the ring ends up with one product only. It just opens up the ring into a linear chain. But if the alkene is not in the ring, when it cuts that alkene in half, it cuts it into two separate molecules. Like that, the two separate molecules here. Right. So for synthesis, you could choose whether or not you want the Hoffman product or the Zaitsev product for E2 by using the unhindered strong base or the hindered strong base. Okay, let's do one more synthesis problem. Here, let's say we have that, and let's say we got this with H. There. Okay. So this is gonna be like related to 118A, like towards the end of 118A a lot. What do you notice about these groups on the product here? We have an OR next to an OH. What reaction do you think this could have came from? Like from 118A, an OR right next to an OH.
Is it like an epoxide?
Yeah, in epoxide opening, where the epoxide is gonna come from these two carbons right here, right? Where the OR is the one that's attacking the epoxide here. The reason why I made these dashes is because, well, it doesn't really matter because when the alcohol attacks, it will invert that dash into a wedge. But it doesn't matter here because we have the plus minus enantiomer as well. Where when the OR attacks the more subside of the epoxide, do we want to be in acidic conditions or basic conditions?
Acidic.
Yeah, acidic conditions. That's right. So we want to use that protonated OR group, which is this OR group protonated in acidic conditions, H2SO4. Right. Now, that is the last reaction there, where that's acidic conditions, alcohol attack the more subside of the epoxide, pop the epoxide on the other side. Where this O here is that O right there. And it would remain as a dash, but I changed it into a flat planar bond because this is not a chiral center. If that was a chiral center, then that would stay as a dash right there. Now, how can we create an epoxide from a double bond? This is the 118B reaction now, or kind of, well,
MC, right? MCPBA.
yeah, that's right. MCPBA, which would just create this epoxide from the alkene there. This synthesis could get more like complicated, more than two steps by, let's say, we had this right here, right? From here, what would be the first step if we wanted to make an epoxide on those two carbons right there? If we had a bromine right there. We know that the previous step was correct, like you got it, MCPBA. We want the alkene right here. But now we have to figure out a way how to make this alkene from this halocane here.
Strong base, strong nucleophile, but this time hindered.
Yeah, that's right. Strong base, strong nucleophile, but this time hindered, like a turbotoxide, because the beta hydrogens are either going to be this one or this one right here. Usually, we want to grab the more substituted one to form the more stable double bond using a small base. but we don't want a double bond there. We want a double bond here to make the epoxide there, to do the epoxide opening here, which is why we want to go for the Hoffman. The Hoffman E2. Hoffman E2. Right. Strong base, strong nucleophile, hindered. Which is going to grab the less sterically hindered hydrogen, make a double bond there, kick out the bromine there. That's right. We don't want the double bond here because we don't want the epoxide there. So we don't use a small strong base. So that's really important. Like the type of base you use to make the alkene, like a small base or a strong base, depending on what you want in the synthesis, like where you want your groups to be. Right? Because for example, if your product was instead say something like that, then we know that the double bond was right there. Right, same kind of reagents, acidic conditions, because the alcohol attacked the more subside, but this time the epoxide is on this side, which could came from the double bond right there with MCPBA. But to make a double bond there, we want to use a small strong base like NaOH. Water. So it depends on what your product is here. For this product here, you want to use the Hoffman reagent. For this product here, you want to use the Zaitsev reagent, right? Mhm. This is Zaitsev. Okay. Any questions on this?
Not for now. Thank you.
Yeah, no problem. I'll create more similar problems to this for you guys to practice for the review session, but hopefully that made sense and helped.
Yeah.
Uh-huh.
For the review session, are we also gonna go over mass spec as
Mass
well?
spec, yeah, like the vocab questions he put on the practice exam. I'll go over those
Yeah.
mass spec questions.
Okay,
Uh-huh.
perfect. Thank you.
Yeah, no problem.
A quick question for
Uh-huh.
the BH3, is that a mechanism that we need to know as well? Because that has multiple steps.
Uh, he did go over it in lecture, but I, uh, like, I rarely see professor, like, I've never seen a professor test the mechanism on that, but this is Pascal's first time teaching 118B, so I'm not really sure for Pascal, but I would know it just in case. And I'll go over it again during the review session because I just went over it like recently and like I'm more
Okay.
like comfortable with this. And then I'll go over it again for this week's review session, the hydroversion
Okay.
oxidation mechanism. Uh-huh.
Perfect. Thank you so much. I
Yeah.
really appreciate it.
Yeah, no problem.
Bye.
Mhm. Yeah. See ya.